So we're going to look at force and motion in one dimension. And the father of force, right, Mr. Newton, right? We can't learn about force and motion in one direction without first looking at Newton's laws, okay? So we can look more specifically at the first and the second law, and later on we will look at the third law, okay? So let's have a look at forces.
He has returned. Newton has returned.
Newton has returned, right? Forces and Newton's laws. Okay, so even Toya, you will remember some of Newton's laws from physics from IGCSE. Okay.
Yeah.
Right. So, well, come, one of you physics buffs, tell me what does the word forces mean in terms of Newton's laws? Right? What kind of forces are we looking at?
Movement.
Okay.
Contact forces.
So we're looking for forces that cause acceleration. Okay. What does that mean to us mathematically, Dominic? What does acceleration mean to us?
It makes one thing, it makes something else's velocity unconstant?
Yeah, well, what do we call that? We have a nice term for that in mathematics. If I have an acceleration is the gradient, which means that I have what in velocity?
You have a change in velocity?
Exactly. That's what mathematically what we've just been looking at. We have a change in velocity. Okay, now that's quite an important observation, right? So if we had no change in velocity, do we have acceleration?
No.
No, then we might have no velocity or constant velocity. Okay? So you will obviously, well, you guys in physics, you will have seen this term before, right? So if we have a net force of 0, we have no acceleration. Okay, so if we have no force acting upon an object, that means that there's no acceleration. So, Toya, give me some examples of forces in the real world that you know about. Okay, and we'll discuss this net of 0. Give me the most
simple ones like gravity.
There we go. Gravity is the granddaddy of forces, right? He's like the guy that everybody thinks about when we think of force, right? Except we know that forces have to be in balance, okay? So who can tell me what, if gravity is pulling you down, what is the force that counteracts gravity?
Contact force.
The contact force of the ground, or
Okay.
whatever you're standing on.
I think technically you call it the electromagnetic force, isn't it? The particles in your feet, they want to resist the ground, and so they push you up.
Well, at the moment we've just been calling it contact force, but yeah, okay.
Yeah, well, you guys will call it contact force, right? It is actually the electromagnetic force, okay? To us layman's people, right? Right, give me some other examples, Kiana. Give me another type of force that you might encounter.
Pressure.
Sorry?
Pressure, upthrust.
Yeah, we got pressure.
Acceleration due to engines.
We have friction, all right? We can have friction forces, we can have tension forces, right? You can have compression forces, right? So there are many types of forces out there, all right? So let's go and have a look at Newton's first law. Right, so there's obviously the very fancy definition for Newton's first law, okay, that you learn when you deal with physics, but we're not really going to go too far into the physics side, so we need some kind of definition that's more relatable to mathematics, right, and what we are studying, okay? So if we have 0 net force, this results, oopsie, sorry. This results in constant velocity. Okay, so Dominic, from a physics point of view, what two types of constant velocity could you have?
You could have constant velocity. Well, you could have positive constant velocity and negative constant velocity,
But
or 0 constant velocity.
there we go. All right, so we could have stationary. Right, so a stationary velocity means that there is just no velocity, right? And the object is not moving. And in terms of constant velocity there is some kind of constant velocity. We can call this uniform straight line. Okay? And the reason we call it uniform straight line is I want you to think back to your displacement if you have constant velocity. Constant velocity means we have a constant gradient on displacement, which means we have a straight line. So constant velocity is either stationary or uniform straight line. Right? So let's think about if we had no force acting on an object, right? It would either remain stationary, or if it was moving, it would be moving at uniform straight line. Now, Toya, I want you to think about the International Space Station rotating around the Earth, right? Is that uniform straight velocity?
Yeah.
Right, well, the answer is no, right? Because we are dealing with velocity, and velocity has both direction and magnitude. So if something is orbiting the Earth, is it going in the same direction? It might have the same speed, but it doesn't have the same direction. It's constantly changing direction, all right? And Kiana, what force is causing that change in direction? Something orbiting around the Earth, there's a force acting upon it to cause this change in velocity, right? It is constantly changing direction, right? Remember, constant velocity means the velocity is remaining the same, right? We could have an object that has a change in velocity. Its speed might be the same. In other words, its speed might be, for instance, if you're driving 50 kilometers an hour in one direction, if you turn around and drive 50 kilometers an hour in the opposite direction, your speed might be the same, but your velocity has changed. There's been a change in velocity, okay? So if we think about something orbiting the Earth, okay, it might be traveling at the same speed, but it's constantly changing direction, which means there's a change in direction, which means there must be some force acting upon it, right? Because there's acceleration. And this force is gravity, right? Gravity is pulling this object towards it, and it causes this change in direction. Dominic, what's the fancy word for Newton's first law? That doesn't look right. Sorry.
It looks perfect.
I'm pretty sure it starts with an E, but I'm not 100%. But I've got
Inertia.
Google. Let me look it up.
It just looks funny because maybe I'm spelling with a little I. Who knows? Who knows? Who knows? But I think that's how you spell it.
Isn't it in the textbook somewhere? Like,
I'm
that's
too lazy to look. I don't like looking at the textbook. There's lots of writing in there. Anyway,
understandable.
so in other words, Newton's first law
It
basically
is an
that
E. I looked it up. It is an
if
E.
we have an object that is at stationary, all right, zero velocity, or is at constant velocity, it will remain like such or at that velocity unless a force acts upon it, right? And so if we take a simple example, if we roll a ball across a table, right, an endless table, right, eventually the ball would stop, right? Not because it runs out of energy, but because there's friction from the table, which causes a change in velocity, right? And it causes the velocity to decelerate, okay? And if we had no friction, that ball would, in theory, continue endlessly, right? Because there'd be no force acting upon it to stop it or change its velocity, right? That's the whole definition of Newton's first law, okay? Let's have a look at, quickly, Newton's second law. Right. Kiana, give me the quick and dirty of Newton's second law. If you had to write it in 5 words, how would you summarize Newton's second law?
Force equals mass times acceleration.
Yeah, that's an equation, right? So here we
If I have to
go.
summarize it into 5, that's a perfect summary.
I'm going to just say this. Force is proportional to acceleration. Okay. That's what Newton's second law is, right? Now, the way you would have learned this in, well, last year when you were doing IGCSE is force, and then you learned this funny little symbol like this, right? Is proportional to acceleration, right? Now, if you remember writing this as y is proportional to x, right? You would have remembered there was that constant k that you always had to solve for, okay? And what is the constant in our case for this example, Dominic? What is our constant with force and acceleration?
With force and acceleration, isn't it V?
No. What is the constant of, if force is proportional to acceleration, right? So as the force increases, the acceleration increases, or as the force decreases, the acceleration decreases. What's the constant, right?
Distance? Or like
Time?
The mass.
just
Oh,
The mass is
Oh.
the constant. Okay, that k that you were solving for, well, in our case, the mass is the constant, okay, because the mass is remaining unchanged. Okay, we are not going to look at examples where something or spontaneously blows out of mass or disappears, okay. We are going to assume that the mass is going to remain constant, right? And so if we say that force is proportional to acceleration, what we're saying is that force is equal to some constant, which in our case is the mass, times its acceleration. Okay? So having a look at this guy here, what do we measure force in, Toya? Can you remember?
newtons.
Newtons, okay? So if we say we have 1 Newton, okay? Right, what is the mass that we're measuring, Keanu?
Kilograms.
1 kilogram. And what do we measure acceleration in, Dominic?
meters per second squared?
Meters per second squared. Okay. So 1 Newton is the force that it takes to move 1 kilogram at 1 meter per second squared. Or alternatively, if you have an object of 1 kilogram and it moves at a acceleration of 1 meter per second squared, you will have 1 Newton of force. Right, Newton's third law, we will save that for another day. So using our knowledge that force is equal to mass times acceleration, we can look at this in some mathematical context. Okay, so we're going to do the worked examples quickly in your textbooks. I would encourage you to, on page 37, there's a modeling assumption there. You know, we're obviously taking liberties here. We're assuming a lot of things are not going to be changing, right? Which is not the reality. So when it comes to these force and acceleration type questions, usually the first thing you're going to do is calculate some acceleration or some something like that, and use it in prior things that we've learned now about acceleration and velocity. Okay. Oops, let's go black. There we go. Right. Question A. All right, it says a cyclist on a bike with a combined mass, so him and the bike weigh 100 kilogram. They accelerate from rest with an acceleration of 0.2 meters per second squared. Find the force the cyclist generates. Okay, so Tuea, what's the equation that we're going to use?
F equals ma.
Okay, F is equal to ma. And we're just going to substitute the values we know, right? We know the mass is equal to 100 kilograms. We know the acceleration is equal to 0.2 meters per second squared. And plugging that into our equation, we get 100 times 0.2. So our force, right, our net resultant force is going to be 20 newtons. Okay, do not forget this guy here. Well, I will tell Mr. T. Right, question B. A second cyclist on a bike with combined mass of 80 kilogram accelerates from rest by generating the same force as the first cyclist. Find her acceleration. Okay, so same question, we're just asking it for a different variable. So, Kiana, are we going to use the same equation again?
Yep.
Yeah, force is equal to mass times acceleration. Right, this time we know the force, right? It's the same force as cyclist A, and cyclist A had a force of 20 newtons. And we know the mass of this cyclist as 80 kilograms, right? So basically we just have different variables. We have 20 equal to 80 times A. And so we can work out our acceleration is equal to 0.25 meters per second squared. Very difficult stuff, hey? Very difficult stuff. Right, question C, right, is going to use Newton's second law, and then we're going to use some of our remembering that when we're talking about Newton's second law, force equal to mass times acceleration, that acceleration is something that we know how to work with. That's what we spent the whole of the last chapter doing. Okay. So the question says the first cyclist is traveling at 20 meters per second, right? Dominic, is that acceleration or is that velocity that we've been given?
That is velocity.
Are you sure? This first cyclist is traveling at 20 meters per second. That is
Velocity.
That's velocity. So
Accel-
that's constant.
Acceleration is, yeah, I
Yeah.
said it was velocity.
Oh, sorry, did you? I'm
Yeah.
hearing things. I'm hearing things.
Oh, well, there's construction happening across the street. So
Tell them to
yeah.
tell them to be quiet. Man. Stick your head out the window screen. Okay, so that's velocity that we've been given there. Okay. Right now he starts to brake with a force of 500 newtons. Find the distance covered while coming to rest. All right, so there's a lot to unpack over there. So let's just state some of the facts that we know. Okay, so we always like to state some information that we know. Well, the only thing we know at the moment is some velocity of 20 meters per second. And we know some force, right, of 500 newtons. Now, Dominic, does force, is it a vector or a scalar quantity?
Force is a scalar quantity.
Are you sure?
No, it is a vector quantity
Right,
because you
because
can have
force has
negative.
direction, okay? Remember,
Yes.
friction is usually happening in the opposite direction of motion, right? Or, right? So force has, very importantly, it has direction, okay? So when we're thinking about force, we need to think about the direction the force is being applied, okay? Now, this cyclist is traveling forward. So Kiana, what is the force in this case, the braking force?
500 newtons.
Is it just 500 newtons? Think about the direction that the force is happening in.
It's 500 plus friction.
Well, let's ignore the fact that there's friction, right? We have a braking force, okay? Is the braking force happening in the direction of motion or in the
No, against it.
It's against it. And so what is my force then? It is?
Resultant force is 480 newtons backwards, unless you still pedaling it.
Well, very importantly, the force is minus 500 newtons because the force is happening in the opposite direction to motion. Okay, so just like velocity and acceleration, we have to treat force as a vector. So we have to analyze in which direction the force is happening, right? This braking force is causing the cyclist to slow down. So the force is happening in the opposite direction. If we had some, like in Cape Town, where they have those horrible gusts of wind, right? If we had a gust of wind coming from behind, pushing in the direction of motion, then the force would be positive, right? So this doesn't mean that there's some very small minus amount of force. This just means the force is happening in the opposite direction. Right, from here we can see we don't have enough information to work out distance traveled yet. We only have a constant velocity at the moment. We need to work out some kind of deceleration or acceleration, okay? Fortunately, we have a formula that we know now. Force is equal to mass times acceleration. Right, because the force happened in the opposite direction, it's minus 500 newtons equal to the mass, which was what was the mass of that cyclist? 100 kilograms. And the acceleration is the thing we're trying to work out. Okay? So here we get an acceleration of minus 5 meters per second squared. Now you can have a look here. If this was not minus 500 newtons, you would get an acceleration of 5 meters per second. And that's what you're saying is that this person is accelerating, okay, not decelerating. And I would hope that if you hit the brakes on your bicycle, you slow down and don't speed up. So the reason it's minus 5 meters per second is because that force was happening in the opposite direction to motion. Right, now we can add that we have acceleration equal to -5 meters per second squared. And we now have enough information to find out our displacement. So, Dominic, which formula would we use to find out displacement, given the information that we have? Because we don't actually have a lot, do we?
Okay, well, we've got initial velocity, we've got final velocity, we've got acceleration.
So which guy do you want to use?
We can use v squared equals u squared
Plus 2.
plus 2as. Wait, is it 2as?
Yeah.
No, it's yes,
You're right,
it's
2as.
2as.
2as. So try to memorize these guys if you can. It does make it a lot easier, because then you don't have to go and look, right? You should just know.
Yeah.
Right, we have 0 because 0 squared, I believe, is 0, equal to -5 squared plus 2, right? My acceleration is -5 s. So we're going to have, I believe, if we move this guy over to the other side, -25 equal to -10 s. What have I done wrong?
Is that 2 times
I'm
8?
using,
or 2 times...
I'm being a dum-dum. I'm sorry. I'm being a very big dum-dum. My initial velocity was not -5. That was the acceleration, right? The initial velocity was 20. So we have -400 on this side. So if we divide both sides by -10, we'll get a displacement of 40 meters. And if we treat the point that the cyclist started braking as point 0, that means that 40 meters from that point in the forward direction is where he stopped.